Hey, what's happening, guys? Today we are going to talk about oscilloscope usage, like a general overview, because I've had guys tell me in the past you don't quite understand, some of the things I'm talking about. So we're going to try and cover that, and today's video is brought to us by Percocet, without which I would be laying on the couch crying. So, moving along. Our oscilloscope is simply an electronic test instrument that displays an electric signal over time. So here in the y-axis, the vertical axis, you are getting the amplitude component of the signal, which in most cases is the voltage. And then in the x-axis, we get the time, the time frequency, Percocet, remember? We get the time aspect of our signal. So why do you want an oscilloscope? What are you using it for? You're using it to three main things: to measure the shape of a waveform, measure the amplitude and frequency, and also to detect glitches in your signal. Okay? Now, you see the grid pattern on there? That's called the graticule. It's the horizontal and vertical lines that display the separation. So in our voltage, we're looking at 1 volt per division. So every vertical square is 1 volt. And then horizontally, we're looking at 8 nanoseconds per division. So every horizontal square is 8 nanoseconds. Now, all scopes have analog input channels. In this case, this is a 2-channel scope. There are 2 analog input channels, and they are BNC connectors. Here's your fun fact for today. BNC is named after the people that created them, the Bayonet Neil Councilman connector. BNC. Okay, whatever. I'm losing my mind. Now, our basic controls for the oscilloscope consists of 3 parts. We have vertical control, horizontal control, and trigger control. Just a little bit. There we go. Trigger controls. So we have a horizontal scale control, and if you can see that, it shows our waveform kind of compressed and kind of expanded. I'm sorry, this is our vertical. So by turning it one way, it gets larger, and by turning it the other way, it gets smaller. So why do we care about this? Well, to get the most sensitivity and accuracy, we want the signal to take up most of the screen without being clipped at the ends. So we want to be right about there. That's our vertical scale control. Now we also have a vertical position control, which can move our signal up or down on the screen. Why would you want to use that? Well, if you're using multiple channels, you might want to put one up high, one down low. Now this little mark over here is always going to show you where your 0 point is. So in this case, this is an AC signal. That's our 0 point, right at the 50% mark. Now we also have basically the same control over here for our horizontal controls. We have horizontal scale, where we can spread out the signal, and then we have horizontal position, where we can move from our trigger point. Why do we need to do that? Well, in a digital storage oscilloscope, it is always taking measurements, but you can't see that on the screen. That's one of the purposes of the trigger. But if you want to see before or after the trigger, you can go ahead and move it with your horizontal controls. Now, I probably should have said this at the beginning, but I didn't. This basic overview is not specific to this Handtech scope. It is going to be for all scopes. The wording might be a little bit different on the buttons, but it's the same thing. All scopes have vertical, horizontal, and trigger controls. Alright, so we finished off with our horizontal control, and then finally we have our trigger control, and that is marked by this little arrowhead over here. That is when it is going to start capturing data. at what, in this case, in what particular voltage, and as long as it is within the signal, we'll get a nice capture. If it's without the signal, weird things can start happening. The screen can start rolling and all sorts of things like that. Now, what's really great about modern digital oscilloscopes when you're just getting started are two buttons, one called auto set and one called 50%. So if you've got an unknown signal, you don't know what the frequency is, you don't know anything about it. If you just basically hit the auto set button, the scope's going to do its best to get you a good signal on the screen. And then again, if you press the 50% button, it is going to set your trigger to the 50% point of the signal. Now, you see how that is shifted up on the screen? We have our 0 point down here. So what we're seeing is a DC signal. Now, within our vertical and horizontal and even our trigger controls, we have menu settings. In this case, we are coupled DC, which means if there is a DC component to the signal, it will be offset by that amount. If we change our coupling to AC, it's basically going to split it right down the middle. And if we change it to ground, we're not going to see anything but a straight line. We'll get into that later. We'll leave our coupling at DC for now. Now, we also have our band limit control here. 20 megahertz band limit is pretty common with these modern cheapo scopes. If you're not using or viewing a signal above 20 megahertz, you can leave that on, and what it'll do is it will filter out some of the crap that's on there. See, there's the bandwidth limit. I can't even tell. Say limit on. Yeah, there's limit off. We're getting the full signal. There's the limit on, and it's filtering out some of the crap. Now, what kind of signal are we looking at here? Well, we are looking at a 28.2 megahertz square wave. Doesn't look much like a square wave, but it does. What you're seeing here are some artifacts, and then we're going to talk about them as well. Now, we also have our probe, whether it's 1x, 10x, 100x, or 1000x in this case. Basically, the type of probes you get with these scopes are 1x, 10x switchable. I would recommend, unless you have a specific reason, you leave them on 10x, both on the probe body and here as well. Now, we also have a signal inversion down here where we can flip the signal. We'll get into that later. That's not really important right now. And then we have our fine and coarse adjustments, which simply change the amount of delta of change when we roll the knob. Okay? Alright, so we talked about our menu settings for the vertical control. We also have menu settings for the horizontal control. I have to shut this light. There, that's better. I can see better now. That light was like blinding me. We have major window and minor window. What this does is it allows you to see more of the signal up here, and then these parts that are specifically blocked off are what you're seeing down below. Alright. Then we also have where we can do some recording, stuff like that, and again, change our positions, just like before. Now, the third menu system we have over here is the trigger menu system. And if I press that button, you can see the different types of triggers. Now, different scopes are going to have many different types of triggers. This one has very few because this is a simple beginner scope. But we're using edge trigger. That's the one you're probably going to use most of the time. There's also pulse, overtime trigger, an alternate trigger, a slope, and a video trigger. Then again, you can determine which channel your trigger comes from, including an external trigger, which is what this BNC down here is for. Now we have our rising or falling edge. Generally you're going to trigger on a rising edge, but you can switch it. And also we have normal coupling, and then we have some filters on here. We can turn on noise reject, high frequency reject, low frequency reject, all of that kind of stuff. So that is a very basic overview of the controls, the main controls. Now there are supplemental controls we're going to get into here in a minute, including measure, acquire, and cursor. But let's talk a little bit about the specifics of oscilloscopes and how they're kind of classified. Okay, when you're looking at scopes, you're going to see a lot of information about the specs of the scope, including a bandwidth, sample rate, and record length. So let's talk about them. Bandwidth describes the frequency range of your oscilloscope, generally in megahertz. And what they're talking about, in this case, this is a 100 megahertz scope. They're talking about the frequency at which it's going to reach its minus 3 dB point. That's the point where the signal is degraded by about 3 decibels of attenuation. It will be at 70.7%. So, as an example, if you were to input a 1 volt peak-to-peak sine wave at 100 megahertz, it would only measure 0.7 volts on here. That's the attenuation. And as the frequency increases, the attenuation basically also increases, and it's going to get smaller and smaller and smaller. So it doesn't mean you can't read a 500 megahertz signal with a 100 megahertz scope. Simply that signal is going to be degraded. The next thing we want to talk about is sample rate. In this case, we have a 1 gigasample per second. So 1 gigasample per second. Oh my god, I should not make videos on drugs. That's not a good thing. Boys and girls, Uncle Paul does not do illicit drugs. Uncle Paul has a specific medical condition called kidney stones, where it feels like somebody scooped out his insides with a melon baller. So, nice doctor has prescribed him a large bottle of narcotics to get him through this until surgery next Friday. Okay, now that we've cleaned that up, let's talk about sample rate. A digital scope samples a signal so many times per second, million times per second, in this case, a billion times per second, all right? And then it has to convert that sample, store it, and display it. The stored signal is visually reconstructed here. That's what we've got. We've got billions of dots here that the oscilloscope has reconstructed to show us our signal. And that's the sample rate. How many times per second the oscilloscope is getting in there and doing that. And that goes hand in hand with record length. It might also be called deep memory, but it's basically record length. The larger the memory, the greater the record length, and the more time a signal can be captured. Does that make sense? You know, having a larger record length allows our scope to capture more. So, you see how tiny this little red box up here is showing us how much of our signal is actually captured? Now see how it gets larger? That's to do with record length. So the larger the record length, the more that the signal you can capture. Alright, let's move on. So we want to talk about our probes. This is the standard type of probe you're going to get with basically any home user type oscilloscope. It is a switchable 1x 10x probe with the BNC connector, and if you look here, you can see down in there is an adjustment screw. That is our probe compensation screw, and I'm going to show you how that works. All your scopes are going to have a built-in square wave generator. So let's connect it. We're going to connect up to the ground first, and then the signal. Then we'll just bring our signal in here. And we have a 1 kilohertz square wave. Now I've already compensated this probe, so what I'm going to do is I'm going to use the tool that they provide. And you always want to use one of these little isolated tools. You don't want to be sticking metal screwdrivers in here. And there's a capacitor in here, an adjustable capacitor. And what we're doing is we are changing the capacitance of the probe. So what you see here is overcompensated. See how we're getting that overshoot there? And that can also go the other way. That's undercompensated. So what we want is to get as flat a line and as parallel a line on the top and bottom as we possibly can. Now again, what we talked about earlier, the switchable 10x 1x, and I told you unless you have a specific reason, leave it on the 1 or leave it on the 10x. Dave Jones at EEV blog did a terrific video explaining why, so I'm not going to reinvent the wheel here and just kind of send you off to his video. I'll put a link to it down below. Now one thing that we definitely want to talk about here is probe usage. Now here's how we're getting our signal on the screen. This is a 10 megahertz crystal oscillator. So we're going to connect up to it, and we're going to connect our ground first. Now this ground lead that you see here is connected to the outer shield of this wire, which is connected to the outer part of that BNC connector. That right there is a direct short to your household ground. You definitely want to keep that in mind, or you'll blow shit up. Now, I've hooked up the ground first. I always hook up grounds first. Then we'll get our signal on here. We'll zoom her in here. And I'm going to put this on AC since it's a sine wave. That way we can keep it right in the middle. Set our trigger. There you go. So far we've talked about everything except the trigger system. And let's talk about that. The trigger system, which is marked by this point here, is where it's going to start reassembling those sampled points of the signal we talked about and showing them to you on the screen. Remember, most signals captured by an oscilloscope are continuous, without end. So if we take a 1 megahertz clock signal, an edge happens every 500 nanoseconds, okay? If the scope were to show this on the screen, it's way beyond our ability to actually see that signal. So instead the scope is going to show us a rolling sample of the signal. Now the trigger allows us to modify when the scope is showing us the data that it is receiving. And there are a number of different triggers. Remember, I showed you the trigger menu before. Now this scope has 1, 2, 3, 4, 5, 6 types of trigger. There's edge, pulse, you have slope, video. There is also, now not on this scope, but on other scopes, you have a pattern trigger, a duration trigger, a setup and hold trigger, timeout trigger, runt trigger, window, delay, nth edge. That's a very useful one. Then you have bus decoding triggers for like RS-232, I2C, and SPI. That's a lot of stuff. Now, we talked about we're basically using the edge trigger, which means we're triggering on a rising edge. So we're triggering on this point here. Now here's our trigger marker right here. So if I were to bring a line right down there, that is the point in which we are triggering. Now we also have trigger sweep, and that's what we have over here. You see where we have our run, stop, and our single sequence. We have an auto trigger sweep, which means no matter what, whenever the trigger condition is met, there will be a waveform displayed on the screen. And the data will kind of be frozen before it goes to the next trigger, but you're not going to see that. Then we have normal mode trigger. In this mode, the trigger holds and it displays the last one. And then finally we have a single trigger sweep where nothing is displayed until an edge is detected, and then it shows us one time, and generally our run stop indicator will turn red. So let's try that. We'll do a single sequence. Boom. Nothing's changing here. This is simply the last one it's shown us, and you see that we've gone red up there. Okay? Whew. Now let's talk about measurements. There are three basic ways that we can take a measurement of a signal displayed on the screen. We can do it by counting with the graticules, we can do it with cursors, and we can do it with automatic measurements. Now, any modern oscilloscope is going to offer you all of these things. So if you come down here and you look, we're at 500 millivolts. Let's make this 1 volt per division. So there is 0. And if we look here, it's hard for me to see, so you're going to have to pardon me. Actually, I'm going to go back. Let's go back. That was my wrong one. So 500 millivolts per division, we are looking at 500 millivolts up, 500 millivolts down, or 1 volt peak to peak on the signal. If I'm seeing that right. Let's verify that. So we can hit our cursor menu, and we're looking at voltage here, so we're going to select voltage, and it's going to come from channel 1, and then I'm going to select my starting cursor, and I'll simply bring it down here right to the top, and then we will select our ending cursor, bring it to the bottom, and you see our delta V is 960 millivolts. I said 1 volt. Close enough for government work, right? Okay, then I'm going to turn off the cursors, because our final method is simply the measurement method. And you can come down here and see our peak-to-peak voltage, 900 millivolts. So three methods to measure the signal on the screen. There are also methods for measuring the time component or the horizontal component, but I think that's enough for today. I think we talked about a lot, and if you're an absolute beginner to an oscilloscope, that's a lot to absorb. So, questions or comments, put them down below. I hope you guys enjoyed the video. If you did, please give me a thumbs up. Feel free to comment, share, and don't forget to subscribe. Big thanks to all the patrons. Big thanks to you guys for watching. Big thanks to Dr. Tan for the lovely drugs. That's it. I'm out. Peace.